Hello everyone, and welcome back to some more Eng 130 final review. So in this video, we're going to be covering the 2016 final, question 3. And as you guys have seen, question 3 in these practice finals are usually always the same, and that is friction, which is going to be no different today. As we see from the picture, we have two crates. Whenever you see two crates, it's most definitely going to be a friction question. So looking at this friction question, it's actually a pretty nice friction question. It's not too bad at all. And there are some tricks that they kind of throw in here to throw you off, but as you guys will see, it's not that bad as long as you know the little tricks. And again, it's probably a fairly basic friction question. There's nothing really too much to really get in your way and really confuse you. So hopefully by the end of this, we can go through and you guys will be confident with crates. This right here, very typical kind of crate question. So if you guys can get this, I'd say that for crates, you guys are good for your final. Again, I don't really know what the final is going to be, but if it's crates and you guys know this one, you guys should be good to go. If it's cylinders, well, that's a whole different ball game. We'll have to cover those. And if it's anything else, like maybe a car or something like that, we'll have to cover those again separate. So for now, we're just going to focus on crates and see how that goes for us. So looking at the question, it says, two boxes, A and B, have uniform weights of 350 kilonewtons and 250 kilonewtons respectively. So what it means is crate A is 350 kilonewtons, but it's actually kind of nice because they put it right on here. And crate B is 250 kilonewtons. So these are actually really, really heavy crates. I wonder what they are, like little houses or something. All right. It says they are stacked on the ground as shown in figure 3. And the coefficients of static and kinetic frictions between the two boxes are, so between the two boxes, we see that the coefficient of static friction is 0.4, and between box B and the ground, the coefficient of static friction is 0.2. So I'm going to highlight box B and the ground, because that's important, and between the boxes, so that's also important. So notice how I didn't highlight the kinetic coefficient I guess not static friction, the coefficient of kinetic friction, is because we never use it. The reason why we throw that into these examples, and I'm not going to say we, because honestly this is such a dirty move that even I wouldn't do it, is because it's just to screw with you guys. Remember, this whole course is called statics. The whole course is statics, everything shouldn't move, and the only time we would use kinetic friction is after things start moving. And as you guys know, we're not dealing with moving at all in this course, so again, that's just kind of there to screw with you. If you guys see they give you two values, the 0.4 and the 0.3 for the between the boxes, for example, a lot of students will kind of scratch their heads and go, okay, well, which one do I pick? And it's going to cause a lot of problems for a lot of students. So please don't worry about kinetic friction. If they give it to you, just leave it be, stick with static. We don't need it. And it says, finally, a horizontal force P, horizontal force P, is being applied to box A as shown in figure. And it gradually increases in value. And it says, so here's kind of the first question. What's going to happen to the boxes? Show all relevant calculations. The effects of the box's thickness, so the dimensions into the page, are negligible. So all it really wants to know in this question, even though it's not really stated very well, is what's going to happen to the boxes. So this is when we're going to have to go through together and figure out all the different scenarios that can happen to the boxes. So let's just kind of draw little pictures and see what happens. So the first one I'm going to draw is this. Let's say that we have box B on the ground. So this is going to be the hardest part of the whole question, is just figuring out what are the scenarios. So we got box B. Now let's say that we got box A on top of box B. So something like this, and we're applying a force P. So we got to think of all the different scenarios that could happen. So I'm actually going to copy this real quick because I'm going to reference this a bunch of times. So copy. So the first one that really sticks out to my head, and to my head, in my head, so I'm actually going to paste this a couple of times because we're going to cover this. So the first thing that happens to me is when I just look at box A, I can see two scenarios happening to box A. The first one is box A just slides on top of box B. So it starts moving kind of to the side. So box A slides on box B, something like this. So I'm going to use orange for the motion. So the motion is just box A slides. And I'll write that down here. I guess box A slides. And the second one that I can imagine is kind of what we talked about before, and that is box A tips on top of box B. So we have this point in the corner, and if, let's say, box A is very slender going up, I can see it tipping. So something like this. I'm very bad at this, so no judging. So I'm going to put this down here. So for this one, box A tips. So those are kind of the first two that I see just off the top of my head. But of course, we got some other ones. So let's paste, oops, that, I don't want to do that. It's not going to work very well. So I'm going to draw these again, I guess. So these are the first two, and I guess I should label these as 1 and 2. Move on, we got to look at 3. So the next thing that comes to my head, and I think a lot of you guys are going to kind of disagree, is I imagine this scenario. So I'm going to draw the boxes. So we're going to have something, I guess this is good enough. You guys aren't going to care too much as long as I show you guys how to do it. So we have our 2 boxes, and we have our force P coming here. And since box A is really, really heavy, it's a lot heavier than box B. What I can imagine is actually both of these boxes will start to move at the same time together as one single box. So I'm just going to draw the dots. Oops, this is not the one I wanted. I want to draw red. So something like this. So this one moves, but box B also moves as well. And you guys can imagine this. Think of something really, really heavy on top of something light, and you push whatever's heavy. Well, the friction between the two is going to cause both to move at the same time. So we're going to have something that would look kind of like this, where they both move at the same time. And for this scenario, we can say that box A and B slide. And finally, the last one that could potentially happen, which it's kind of funny, but it could definitely happen, and I got to draw these again, I should have copied them, is since box A is so much heavier than box B, oops, if we have a box that's so much heavier and they act as one single unit, there's the possibility that they may both tip together. I'm just going to draw these real quick. So even though it seems kind of hard to imagine, there is a possibility that when we put this force up here, and these boxes are very, very heavy, but very, very high up, there's a slight possibility, and I say slight, that they actually tip together. So it'd be something like this. And forgive me for taking so long. I know you guys don't really want to watch me do this, but part of the fun. So let's say that they both tip together. So this is my fourth one, and I say box A and B tip. So now I know a lot of you guys are gonna, Clayton, hold up. So you did box A by itself. You did the 2 cases, that's fine. You did box A and B. Well, it's a little bit weirder, but still that's fine. What about just box B by itself? And I'll have a lot of students saying, can just box B slide and nothing else happens? Well, let's just draw a picture of what that would look like and see what happens. So we have box A right here, just like this. So we got box A, and we apply the load on it. So in my head, and I'm not sure about your guys's, but it'd be very difficult if we applied a load onto box A and we somehow had B moving. So you guys, oops, I kind of zoomed in. So you guys see what I mean by this picture? If we apply it at point A, it's very hard to see this box start to move because of the load at A. It's impossible. So this isn't a scenario where box B moves, but box A doesn't. So in general, we got these 4 scenarios. And what we're going to have to do is we're going to have to find the force P, which I should probably label on all these actually. Let's put them in there for fun. P, 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 P. So we have to find the force P for all these scenarios to cause these to happen. And it's actually not too bad because remember, the trick for friction is if we have a good free body diagram, we can solve for everything. And this is why I like to draw these scenarios, because with these scenarios, we can figure out which free body diagram to draw, because we actually have 3 free body diagrams we can draw. The first one is box A by itself. The second one, box B by itself. And then the third one is box A and B together. Now, with friction, it's kind of common where you can draw more free body diagrams than you actually need to. And that's the same in this case. We have 3 free body diagrams, but we only actually have to draw 2. And how do I determine which 2? Well, I just look at my scenarios. For the first 2 scenarios, just box A is moving. So one of the free body diagrams should just be of box A. And in the third and fourth scenario, we have box A and B moving together. So what that tells me is my second free body diagram should be boxes A and B together. And we've also concluded that box B will not slip by itself. So therefore, we should not need a free body diagram of box B whatsoever. We need a free body diagram of box A and a free body diagram of boxes A and B. So what I'm going to do is I'm just going to come down and I'm going to say free body diagram. Remember, our first one that we said was we're just going to do box A. So just box A by itself. So it's actually nice and easy because box A is not too bad. So we're going to draw just a simple box. And, oh, that's why. I'm slowly learning. Here we go. Okay, so we got a nice box. We might as well line it up on the grid. Why not? And we have to keep in mind that when we're putting our forces on this box, we have a force P acting on this box up top. And this is our goal. We want to find out what force P is. So if force P is pushing the box to the right, we know that the box is going to start moving to the right. The box itself is going to start doing this. So if the box is moving that way, well, that tells us that the friction must try and counteract that movement. So the friction is going to be going the opposite way of P. So we're going to have this as the friction. And of course, with friction, we always have a normal force accompanying it. So we're going to have a normal force here, like this. And then, of course, the box has a weight. So we have a weight coming down right at the centroid. So I have a weight coming down, and we know that the weight is 350 newtons. So what's actually kind of nice, but also at the same time, as we'll see, kind of bad, is we only have 3 unknowns. 3 unknowns, but here's one of the problems. In these type of questions, when it's just sliding, we usually don't use the moment. So we technically only have 2 equations. We have some of the forces in X and some of the forces in Y. And I'm just going to add dimensions really quick because that's always good to have. So we have 4 meters at the top here. We have 3 meters. So we have some of the forces in X and some of the forces in Y. So we need a third equation. And if we recall, we actually said something very important. We said, in one of the scenarios, box A slides. And if this is true, what that means is that F is equal to mu times N. And remember, we're only interested at the point at when sliding just begins. When sliding just begins. So when we're dealing with the U here, it's going to be the static one. So if we look up here, between the 2 boxes, U box S is equal to 0.4. So right in here. So when we come down, we can go F is equal to 0.4 times N. And now this gives us a third equation. So now we have 3 equations, 3 unknowns. We can start solving things. So looking at this, it's actually not too bad. What we can do is we can go with sum of the forces in Y is equal to 0. And it's very obvious because what we get is the normal force minus 350 is equal to 0. So we just move that to the other side and we can say that the normal force is going to be 350 newtons. Or kilonewtons. Is it newtons or kilonewtons? I should probably check. it is kilonewtons. So this right here, I need to erase this and put kilonewtons in. So like I said, these are very heavy boxes for some reason. I don't know why. So 350 kilonewtons. And now that we know this, we can use our equation for friction to determine the friction, because friction is equal to 0.4 times the normal force, which we now know is 350. So when we throw all that in, what we get is the friction is equal to 140 kilonewtons. And now we can finish off everything by going sum of the forces and x is equal to 0. So this is just as easy as before, because we have P going to the right, we have friction going to the left, so P minus F, and that's it. So it's equal to 0. So therefore, P is just going to be equal to F, which is 140 kilonewtons. So what I'm going to do here is I'm just going to highlight this, because this is not our final answer. Remember, this is just one of the cases. So for this case, I'm just going to highlight it right here so I can come back and check what happens. And actually, what I'm going to put underneath it, just to make sure I remember which case it is, I'm just going to say box A slides. So now when I come back, I can say, okay, the force required to make box A slide is going to be 140 kilonewtons. So that's actually pretty low, and we can see if we can find something lower than that. So the next one we're going to check, because it's going to be the same free body diagram, is I'm going to put this, and I'm going to go box A tips. So again, we're just looking at box A, so we still just use this free body diagram. We have box A tips. So remember, if it's tipping, it's going to tip on that opposite point. So I'm going to highlight in purple. It's going to tip about this point right here, which is point, we'll just call it point O. And to find tipping, what we always do is we take the sum of the moments at point O. So what we're going to do is we're going to go sum of the moments at point O is equal to 0. So if we look at this, what we're going to have is we're going to have P creating a clockwise moment, so it's going to be negative, and it acts at a distance of 4 meters. So we're going to have negative P times 4 meters. And then a lot of people say, okay, well, we got a normal force acting halfway across, but we actually don't. So this is one of those tricks that can, again, get students, because when something starts to tip, and I'll draw it here. So let's pretend that this blue line right here is the ground, like this. So when something starts to tip, the box is going to come slightly off the ground. So ever so slightly off the ground like this. So the normal force actually transfers to the end. And we're taking the moments about that end point, so it's not going to create a moment. So that's not going to create a moment, and the friction will also not create a moment, because it will also shift to the end. So the only other thing that's going to create a moment in here is going to be the weight. And we see that the weight creates a counterclockwise moment, so it's going to be plus, and then the weight's 350, and the distance between that point and the weight is just going to be the 3 meters divided by 2. We're going to have 3 meters divided by 2, and this is all equal to 0. So if we look at this equation, we have P, and that's it. That's our only unknown. So we can solve directly for P, and we can say that P, in this case, is equal to 131 kilonewtons. And I'm going to put in brackets box A tips, just to remind me what scenario this is. So box A tips. I'm going to highlight this. So far, looking at the two cases, we know that box A is going to tip before it slides, because it requires a lower P value. However, we're not done yet, because there's other situations we need to analyze. So we're going to come up here and we're going to go free body diagram 2. So I'm going to go 2. Oops, that's not what I wanted. I want to go 2. So my second free body diagram. And this one's going to be box A and B. So for this one, what we're going to have is we're actually going to have the two boxes stuck together. So I'm going to, I don't know, we'll do something like this. May not be the perfect free body diagram, but it'll be good enough. Alright, so we got boxes A and B. I think it's pretty clear. putting on some loads, it's going to be the exact same where we have a force P applied at the same spot. And we're going to have friction trying to resist it at the bottom. This is going to be the same motion. And of course we have a normal force. And then we have two weights. So we're going to put the weights in right here. So the top one we remember is 350 kilonewtons. The second one is 250 kilonewtons. And the bottom one, of course, is the normal force. So we got all those in. The last thing that we should do is just put in the heights or the dimensions. So we know that the first one is 4 meters and the second one, sorry, box A is 4 meters tall. Box B is 5 meters tall. So we're going to have 4 meters, 5 meters, and we should also include the horizontal distances. So we kind of had 2. Box A is 3 meters and box B is 5 meters. So in the end, what we have is we have 3 meters and 2 meters. And if we look at this free body diagram, it's done. So remember, if box A and B are sliding together, and I'm going to put this, what color did I put this in? Because I'm going to put in the same, the kind of the dark green, like a tree. So we say if box A and B slide, well, therefore our friction must be equal to mu times n. And in this case, we want the coefficient of friction between the ground and box B. So we come up here and it says the coefficient of friction between box B and the ground is 0.2. So this part over here. So we're going to use 0.2. So in this case, the friction is equal to 0.2 times the normal force, just like this. So it's not too bad. We have our third equation and we have 3 unknowns, so we can actually solve for everything right away. So just like before, we're going to start off with some of the forces in the y. And if we do that, what we get is we got the normal force acting upwards, but then we got the 2 weights of the blocks acting downwards. So it's going to be minus 350, minus 250. And this is it. So everything must equal 0 because it's in equilibrium. So solving, we get the normal force is equal to 600 kilonewtons. Okay, well that's not bad because now we can throw that into our friction formula to find their friction. So our friction is going to be equal to 0.2 times the 600. And when we do that, we get that the friction is equal to 120 kilonewtons. And when we go sum of the forces in sum of the forces in x is equal to 0. It's the same as before. We get that the force we apply P minus F, the friction, is equal to 0. So if this is the case, our P force is actually equal to F. So therefore we can say P is equal to 120 kilonewtons. So this is the lowest one so far. So right now, this is going to be the case that governs right now. So this is box A plus B slide. Got to throw that in there. And I'm going to highlight it so we can check it later. So far this is the governing one because it is the smallest out of the 3 cases we examined, because before we got 140, 131, but now we got 120. So this is so far the governing case. However, again, we need to check the last one, and this is case number 4, which is boxes A and B together tip. A plus B tip. And this is always very easy. We're always just going to take a moment. So if we look, it's going to start rotating around that opposite corner over here, which we're going to call point O. So we're going to come down here and we're going to take the sum of the moments about point O. So sum of the moments about O is equal to 0. And just like before, we got P creating clockwise moments. We're going to have negative P. But now it acts at a higher distance, which is going to be 9 meters. So the 5 meters plus the 4 meters. So P times 9. And if we look at the weight at the bottom crate, it's going to be the 250. And it acts at a distance of 5 meters divided by 2. So we got plus 250. And we got 5 meters divided by 2. So far, so good, not too bad. But then we got 350 kilonewtons. And this is what's going to confuse students the absolute most. This is 350 kilonewtons up at the top. So I'm going to get a different color right here. Because this is what came into my mind, and I'm sure this is what came into a lot of your guys' mind, is once this starts to tip. So I'm going to actually copy this, and we're going to analyze it from the bottom. So I don't need dimensions or anything. So let's just, I guess we'll take dimensions. It'd be weird to include them in one, but not the other. So we're going to take this, copy, we're going to come down here, and we're going to paste it as a picture, I guess. Interesting. All right, so if we have this case scenario, what came into my head is, let's say that as box B tips. So we have box B now tipping like this. And this is exaggerated. Remember, the point at which it first starts tipping, it's just barely off the ground. You won't even be able to see it. But this is kind of the scenario that came into my head. So as this tips, I imagine a scenario where A starts to slide down box B. Like this. So we see that A started to slide down box B. And if that's the case, then the weight is actually going to shift down box B as well. So this was my kind of first impressions, and I was thinking, okay, well, this is really confusing because where does the new weight act? But I realized this is never going to be the case. And the reason why is this, and I'm sure a lot of you guys have already figured this out, and I'm just an idiot, but it's because if box A is sliding, well, then that's the case up here. That's the case all the way up here. Box A slides. So we actually already covered this case. So for assuming tipping right now, we have to assume that box A does not slide. And if it does slide, well, that's not this case at all. That's actually this case up here, which we have already checked. So in this case, we're assuming that box A actually stays on top of box B, right in the point over there. So what it's going to be coming up here. The distance that we want, and I'll do this in kind of the dark green, is going to be this distance right here. So we know that this distance from the edge of box B to box A is going to be 2 meters. And then the distance from the edge of box A to the center is going to be 1.5 meters. So we know that the total distance we're going to have here is 3.5. So we're going to come here and we're going to write 3.5. And this is all equal to 0. So when we solve this one, because P is our only unknown, we get P is equal to 206 kilonewtons. So as we see, box A would actually slide before they both tip together. So it's kind of expected, you kind of see it in your head, but we had to check this case anyway. And this case right here is box A plus B tips. So now we just did all of the scenarios. So what I like to do for these, and I know that the markers will really appreciate this, is if you just make a quick little summary. So for the summary, we got the scenario, and we got P in kilonewtons. So the scenario, we had box A slides, and we know that this was 140 kilonewtons. We got box A tips, and this was what, 131? Yeah, 131 kilonewtons. And we got box A plus B slides, and this one was 120. And we have box A plus B tips, and this one was 206. This would require a lot of force, and again, this clearly won't govern. So our governing one is going to be the one that happens at the lowest P. And if we look at this scenario, well, this is going to be this. 120, that's the lowest value. So therefore, box A and B slide together. So just as a final answer, what you should do is you should say box A plus B slide together. And then what we should do is we should also include the force. P is equal to 120 kilonewtons. So as soon as P reaches 120 kilonewtons, then we're going to have some movement, and that's those two boxes are going to move together. So we're going to box our final answer. Get it? We boxed the answer, and we're dealing with boxes. Terrible humor. I bet one of you is laughing, but the rest are thinking, what a cringy guy this is. All right, but that's it. So again, this question, not too bad. People always hate friction because they kind of have to play guess and check with it, figuring out what kind of scenario is going on. As you guys see, we just have to picture the scenarios. From the scenarios, we draw our free body diagrams, and then it's just using equilibrium to solve for everything. So it's not too bad. So I hope this helped you guys. This question wasn't too bad. There's going to be a lot worse questions that we're going to go through, so hopefully this was nice with you guys. So thank you guys all so much for watching the video, and I'll see you guys in the next one.